So my name is Radovan, and I'm really looking forward to discuss this topic now with you for the next 2 hours. Don't worry, we will take a break halfway through. I work in Tromsø at UIT, doing support in everything around computing, high-performance computing, programming. I really like helping researchers with their computations and with their programming and data management. And since I also come from research, I know how it feels. So I know that some of you are completely new to high-performance computing, and that is really not a problem at all. I know that some of the concepts that I will introduce will be new, but I will try to keep it really understandable. This is not a complete introductory course into how to navigate on a command line, how to set up a job script, but still I think it will be useful for everybody, even if they are completely new. And just as a reminder, also for Daniel said, so the best way to follow is to switch off your microphone, switch off your camera, because then you are sure that to not appear at all in the recording. If you accidentally do, we will edit it out. And the best way to participate is through this document. So you find the link in the Zoom chat. Please go to this document. So there are here, I see there are 30 people online. That's great. Please click the edit button and please do edit it. Not only here the icebreaker questions, but also later when you ask questions. So if you scroll down here, this is then the best way to ask questions. It's better than over microphone because you don't end up in the recording. It's anonymous. And also we see that if we provide people with the opportunity to write questions in writing, we see that we get many more questions than we would in voice. And if you ask lots of questions here or add comments, then you give me a feeling that I'm not alone here because I'm just really talking here to the camera. And I can see that 35 people are in this call, but it will feel also better to me. And I'm watching these, so on a different screen, I have these open. And I will try to answer all of those that I know how to answer. I have also colleagues here with me who will help me answering these questions in writing. So please do ask lots of questions. Nothing is too simple. And I put here links on material that we will cover today. Today I will show you what techniques I use to figure out how much memory my job needs and how many cores my job needs, and I will also tell you why that matters. And everything I will tell you, you can find in this documentation. So you can also go through it later on your own time, which I recommend to do. I will demonstrate a few things directly on the cluster, but I recommend to watch what I do. If you really want to type at the same time, you can. And you can find the examples that I will use in these places, but I recommend to just watch and ask questions. Okay. Excellent. And just to give a setting for what we want to do today, I will pull up my terminal here. Just a moment. And I want to show you what we are after. So here I'm on one of our clusters called Saga, and I want to show you a run script, a job script. So when you run calculations on the clusters, and if you are new to this, you will do that soon. You will always have to specify so-called run script or job script. And here is an example for such a job script. And what we see here is before you even run your calculation, and instead of here running my binary, you run your example, which can be a Python calculation, R calculation, something else. You need to specify a few things, like the time, how long should the job run, how much memory do I need, and how many cores do I need? In this case, in this example, I'm asking for 1 core. I'm asking for 1.5 gigabyte memory, and I'm asking for 1 minute 30. And today, so the next 1.5 hours are really about why does it matter? Why is it really important for you and for us? So that's question number 1. Question number 2 is how to know, like how do I know? Should it be 1.5 gigabyte or 4 gigabyte? Should this be 1 core or 100 cores? How do I find out? And it's not easy, but I will show you some tools and techniques that help me answering this, and that will also help you answering this. Does that sound good? And of course, you have no way to answer now in voice, but I'm also looking here at the icebreaker. Here would be nice to have more answers. So this is exactly the question. So how do you do this? How do you specify the total time, the number of cores, the memory? And I'm not so much here interested in how do you do it, how do you specify it? Not so much in this part, but like how do you choose the number? And here I have 2 answers. Well, we start with a guess and we adjust. I think that's a good technique, and this is also something I will show. Or I think there was an answer, but now it's coming back, that I inherited a script from a colleague and I left it as it is, and it just works. Or not sure, and that's why we are here today. Excellent. So if you have answers, please give them. Honest answers, really welcome. And now, why does it matter? And for this, just as a starting point, before even going into the terminal and showing you the tools, I want to start with doing a little drawing. Let's see how that goes. I'll just make this a bit more clear. I will start by making a drawing on a whiteboard here. Let me know if the font size is not good or if the volume is not good. Here, let me do a little. So, okay, this is not very beautiful, but often we have to make the choice. So I want to show you how do jobs look like, really. So we have time and we have number of cores. And I want to start with, so some jobs they take a long time, a week, but they don't use many cores. So they look like this. I mean, okay, this is freehand with a mouse. So imagine that this is a nice rectangle. Then we have other jobs which can be more wide. So there are other jobs that use lots of cores, but maybe they only run for 1 hour. And here is another job. Okay. And what I want to tell you here is that on a supercomputer, jobs are like little rectangles. So there is a time and number of cores, and you submit these jobs to the queue. It's like a waiting line, and the supercomputer tries to run them as soon as possible. And what the supercomputer does is, you can imagine if you know the Tetris game. So pieces fall from the top and then you try to arrange them so that you fill up rows completely. This is really exactly what the supercomputer is doing. So what the supercomputer tries to do, it tries to keep all the processors busy all of the time. So it plays Tetris all the time. So there are these rectangles falling from the sky. These are your jobs. And it tries to arrange them so that everything is full all of the time. What you are interested as a researcher is that you want your job to finish as soon as possible. That's what you want, because you are interested in the result. And now guess what happens if, I will now do a little highlighter here. Here I have a job that I told the scheduler this will take a week and it will take a couple of cores, but imagine what happens if the job, it doesn't actually take 2 weeks or 1 week, it finishes after a few hours. So some jobs ask for a lot of time, but they don't use a lot of time. So what do you think will happen then? So the job stops here at this moment here. And one question that we get often is, well, do I have to pay for all of it? Also the unused time? No, you don't have to pay. So you only get billed for really this part here. But the problem is that the scheduler doesn't know it. It tries to play Tetris. And if you ask for too much time, you risk of being in the waiting line for too long. So what would have been better here, if I know that my job takes only 2 hours, what would have been better is to request something like this, a little bit more than what you, like 20% more. So that's about time. But now the same argumentation is about number of cores. We see many jobs that ask for lots of cores, 40 cores, 100 cores, but then they end up using maybe only one. And all of the other cores are idle and they do nothing. But you still get billed for them because you block the resources. The resources cannot be used by anybody else because the scheduler, the supercomputer, doesn't know that you are only using one core if you ask for 40 cores or 80 cores. So and today we want to really talk about how to choose this part here. This part, how wide should it be? And I will also scroll to the right side because a similar question exists for, for the memory. So we also need to choose memory. And really very similar things. So also from the memory perspective, jobs are rectangles. And we need to find out how much memory we need. And why does it matter to choose a okay amount? Because the left side and the right side, they are not completely decoupled. Why is that? I will go to our documentation sigma2.no, and I will go on one of these clusters, for instance, Saga. And here I can find out that we have so and so many compute nodes. So there are 200 compute nodes. Each of them has 40 cores and a certain amount of memory. So one compute core has approximately 4 to 5 gigabyte memory on this cluster, which means that these two are not independent. If I ask for a lot of memory, I don't use it. Let's say that maybe I only use a little bit here. Then all of the rest is unused, but maybe I'm blocking CPU cores that other people could be using, and I'm getting charged for them. So number of cores and memory, they are coupled to each other because the memory is sitting on the CPU core. So if we still think in terms of Tetris, then I could maybe draw it as a 3-dimensional. They are like little bricks. So one side of the brick is the number of cores, the other side of the brick is the memory, and then the supercomputer plays Tetris. And I still don't see any questions here, which means that what I say is maybe way too easy or way too difficult. So please ask questions and give comments. So we will do today so this will be part 2. Is number of cores. I want to start part 1 is memory, how much? Whoops, this is really ugly. This will be part 1. I think I want to show you I want to mention one more thing that is good to know. I will go with the eraser here. And that is that I told you that jobs are rectangles or little bricks. But in reality, so here I allocated the job over a certain amount of cores for a certain amount of time. But in reality, if you look inside the job, some jobs, they, at the beginning, maybe they use only one core for a while. And then after a while, they start to use lots of cores for a while. And maybe at the end, they again go back to only using only one core. So this is, imagine that this is full. And what you allocate and what you get charged for is actually the area in the jobs. So these rectangles, the area is the resources that you really use. But what do you do with jobs like this? Inside, they are not really rectangular. And the same thing, I could draw the same thing for the memory. If you look at the memory, it can vary. At the beginning, maybe the job uses a lot of memory, but over the time, it uses very little. So what should I do here? And this is maybe a little bit more advanced, but I want to just mention that what I would do in this case, I would try to maybe chop up the job into 3 parts. Instead of doing this in one step, I would do this step, and there I only need to allocate this. I would do this as a second step where I allocate a lot, and then I would do this as a third step. But how to chop jobs into pieces and how to make them depend on each other is for a different course. But I think this is just good to know. And thanks for the first question. I don't recall specifying memory in my jobs run script. What happens then? So if you don't, depending on which cluster you are, and today I will work on 2 clusters. I will start on Saga, where you have to specify the memory, as far as I know. Otherwise, the job doesn't even queue. But on other clusters, you don't have to. And then it takes the default. So if you don't specify anything, it will typically take the amount of memory that the CPU has, which is okay. The problem is more that if you specify way too much, then other CPUs will borrow, they will donate their memory, and you will block these resources. So I wonder whether this was somehow clear. So jobs are rectangles. The resource that is used is the area in the rectangle. And we need to today learn how do we specify the number of cores and memory. And it matters because it will determine how long your job is in the waiting line. If I ask for way more than I need, it will be in the waiting line too long. And if I ask for way more than I need, I also get charged, like my compute account will be charged more than I would need. And I will now start in looking at this case, memory, how to specify the amount of memory. And for this, I will go now onto the cluster, but I'm watching your questions, so please keep them coming. I will keep this open here, but I will now move to the cluster, and I will also make sure that you can see the commands that I'm typing. So whenever I type something here on a cluster, wait a second, I need to adjust this a bit. Whenever I type, the last command will show up down here. So if I'm typing a little bit too fast, and if you really want to type at the same time, you can see what I'm doing here. But I recommend to watch. So question number 2. So if I need less memory than what the number of cores can provide, what should I do? Then you specify memory like I will do here. Here in my job script, I'm specified that I want to have 1,500 megabyte per CPU, which here happens to be actually less than what the core has available. I think the core has 4 point something gigabyte available. I wouldn't worry too much if you need less than the CPU has. I would start worrying when you need a lot more. Because if you need a lot more, it might also be a moment to go. Let's go to Saga. If I need a lot more memory, then maybe you don't want to be on the standard compute nodes. Maybe you want to be rather on the compute nodes with medium memory or big memory or huge memory nodes. So we have compute nodes which have enormous amount of memory, and then maybe you want to move your jobs to these partitions and these compute nodes. So now my plan for the next 20-30 minutes, and then before we take the break, is to learn how do I figure out this number. And I will work here in the terminal, and I will type, and I will maybe make mistakes. So if you see something wrong, then please point it out on the document. But I will really follow. Oh yeah, I want to show you where you can find what I will follow. I will follow our documentation. So everything that I will show you find in our documentation. The 2 pages that I will use are in the collaborative notes, but I also want to show you if you lose everything, the notes, and you want to find it again, I can show you how I look for it. So documentation.sigma2.nl, whenever I want to find these things, I go on, we have these tiles, getting started, getting help. Here, job types and scripts. I click on the tile, and you can already see this is different color because these 2 I click all the time. How to choose the right amount of memory. This will be part 1, and how to choose the number of cores. And if I go in here, then it also motivates again. Why is this important? Why does it matter for you, but also for us? Because if you choose better settings, we get better use of our resources, and there is more science and applications and publications per minute CPU cycle. That's what we really want. And all of these strategies that I will show you, they are all listed here. So you can test it out later in the afternoon or some other day. Back to my example. I have here a binary so it's a program that I wrote, and we can imagine it's a black box. We don't really see what is inside. We got it from somewhere. I got it from my colleague. I don't know how much memory I should use for it. Here in the README is like a description of what I should do, but I will just tell you in voice. And I have a job script, and I showed you the job script already. So in this job script, 1.5 minutes, I'm just guessing here, 1.5 gigabyte. And I will now try to run this job. And the way we run jobs on our supercomputers is that I submit the job to the queue, so to the waiting line, and then I let the supercomputer who plays Tetris to put my rectangle somewhere and let it run. And the way I submit my job is as batch. It has been submitted. It will run for approximately half a minute, I guess. I can watch, oh no, SQ, with SQ --me, I can see all the jobs that belong to me, and I can see their status. So this one, there is nothing here. I was expecting that this would be running for a while, so maybe it crashed. Let's see what happened to the job. I got an output from Slurm, which I will have a look at. So with the cat command, I can display what is inside the file. Let's have a look at what is inside there. There is lots of stuff. So when was it completed? When did it start? Some numbers. The thing that I can see here, and which is not easy to see when you are new to this, is that I can see that something went wrong. This doesn't look good. The job has been killed by the scheduler, and for what reason. This is maybe also not so easy to read, but what I know now is that the OOM is not a good thing. I wish there was a better error message, but OOM means out of memory. OOM, out of memory. So whenever you see this, I wanted to show you how this looks when you ask for too little memory. This job didn't have enough memory. As soon as the job tried to use more memory than I asked for, the scheduler immediately stopped it. So it stopped after 2 seconds. So what to do next now? VI is my editor. Maybe I shouldn't use VI. Maybe I should use Nano. So there are different text editors that you can use then on the cluster. I will use Nano, which is simpler. So now what I should do, I should really change this number. And now I will ask for a number that is maybe a lot more than I need, because now I'm a bit desperate. So this is not enough. I don't know how much it needs. Let's ask for, I don't know, 4.5 gigabyte. So how do I save it? Control X, yes, save. I will try the same thing again now with a lot more memory as batch. And again, sq-me will show me my jobs. Now it didn't immediately crash, so that looks promising. It's running, we are 10 seconds in. And it's running, it will, I'm very optimistic that this one will complete. I think it will complete after like 35 seconds. And I will later tell you also why I made it so that it stops after 35 seconds. So now the job completed. Let me show you how a Slurm output looks which didn't crash. So what is this here? This is the number of my job. So each job that is in the waiting line or is running gets a number. And I can refer to it then by the number. And let me open the output. So there is some statistics. There is no crash in this one. It tells me this went for 37 seconds. What is this wall clock? Why is it called wall clock? Because that's like the time with a clock on the wall. So this is the actual time that the job has used. There is some more statistics here, which I will tell you how to read it, but at least this finished. But now I probably asked for too much. So I would now like to show you some strategies on how to find out where between 1.5 gigabyte and 4.5 gigabyte, how do I find out how much it really needs without trial and error? Of course, I could now decrease it, run it until it crashes, then increase it again until it doesn't crash, but that feels tedious. And thanks a lot for the questions. So I will start with question number 4. What is Slurm? Slurm is the scheduler. It's the program that will decide. It manages the waiting line of all the jobs, and it schedules which one can run to make the most use of the cluster. So if you imagine like going to a restaurant, and let's imagine you don't have a reservation, but you come there and you want a table for 4 people, then Slurm, imagine that that's the person you talk to. It's the person who looks into the books and tells you that, well, yes, we might have a table, but you might need to wait half an hour. So that's Slurm, and it's an abbreviation, and I forgot. I think the S means simple, maybe Linux. I don't know what the rest means. Do we have any AI tools which can look at the code and suggest something? We don't yet. I think it would be a fun project to write. I still believe that it's difficult, and probably the best person to answer this question is you, because you know your job the best. And the tools that I will show you, I think this will still lead to a better answer. But AI might solve it soon or one day. So now my goal is I want to find out what is it actually using. And again, as a reminder, I will the techniques that I will show, they are all listed here. So I will scroll up. So one thing that I can do is, and I just want to make sure that I don't forget anything. One thing you could do is you submit the job again. Let's just submit it again. Let's do sq-me again. And while it is running, if I'm really quick, if I'm faster than 30 seconds before it stops, one thing I could do, I could log in, I could connect SSH, I could connect to the compute node where this is really being computed. And on the compute node, you can type top or htop. Let's see whether this works. No, htop doesn't work. Let's try top. And top will show you what is running here. Do I see my job here? What if I do top user me? Then I only see my jobs. This one is my job. I think it is my job. No, my job might have already finished. I have a feeling that my job already finished. But if I'm quick enough, I can catch my job here. I can see how much memory is using, the percentage. And also from these numbers, I can see not only how many CPUs it's using, also how much memory it's using. This is not the easiest way. I only wanted to show you that this is a possibility that exists. I think it's more interesting for the number of cores. I will show you easier ways. So I go back from the login node, sorry, back from the compute node where the computation was actually running. I'm going back to the login node where I'm submitting jobs. I want to show you some better ways where you don't have to be quick and you don't have to log in anywhere else. And one of these ways is, if I know the job number, one thing I can do is, there are different commands, and you can then remember the one of your favorite ones. So one command we have is job stats, job statistics. And if I give it a job number, so the job doesn't have to be running, it can be a completed job now. It will give me the same statistics that I saw in the output of Slurm. And maybe I can find out from here. So I think this is interesting. Memory statistics in gigabyte. I have allocated 4.5 gigabyte, but I have used 3.1. So this is the amount that I have really used. So a good way to ask for memory would be to take this number and then now add 15%, 20% to it, just in case. That would be a good setting. Another tool that we have is called Ceph, and I think it comes from Slurm efficiency summary. And again, if I give it the job number, if I remember the job number, it gives me a nice summary of what the job it completed. Wonderful. It didn't use a lot of CPU, so I asked for 36 seconds. It actually only used very little of it, but this is now not our concern. We will come back to that after the break later. Now our focus is on memory. And this thing tells me that I have used 3.06 gigabyte. In other words, I have used 70% from the allocated 4.4 gigabyte. So that's another way to find out. And thanks for question number 5. I will come back to it in a moment. I just want to show you one more tool that I really, really like, and I wanted you to know about it. If I go back to my run script, instead of running my calculation here, and instead of my binary, it could be, you know, Python, your script, or it could be something. So whatever is in here, in front of it, you can write USR bin time -v. So whatever you do, you can prepend it with this. This will not only give me timing, but it will give me very detailed information about how memory was used, even more detailed than what I've seen here. So I will try this. Oops, sorry, I will save. And I will submit it. And while it's running, I will try to look at the questions. So let's send it to the job queue. Let the computer do its thing. Now let me go to questions. So what if the files I input to my script change, and thereby also the memory needed changes? Yeah, I think that's a very good question, because so what I do here is calibrating how much memory I need. But I'm assuming, so often I have like 100 jobs, 100 calculations to run, or 50 calculations to run. Very often the calculations that I have to run have similar resource requirements. And if they have similar resource requirements, I only have to do this calibration once. And once I have calibrated, then I can submit all my 50 jobs. But if I have different jobs with different requirements, I might need to do this more often. And of course, there is a trade-off, because this calibration also costs CPU time. It also costs your human time. So you need to then decide, is this a good trade-off? But very often it is a good trade-off, especially if you plan to submit very many relatively similar jobs, then it can really pay off to do this calibration. But sometimes it can be difficult to tell. It can also be just difficult to predict. There are calculations where for each calculations, this is just different. And then you may have to go for a very conservative guesstimate. You can also contact us and ask us for help. So if you are unsure, like I have this job and I'm just really not sure what I should put here, you can send us an example and we can look together with you. So let's see whether my job completed. Skew me, my jobs, nothing is there. It probably completed. And I got, sorry, no, I shouldn't do V. I want to look at the Slurm output. This is my latest job. You can see maybe that this is bigger. So there is more in the output. Now there is more details. And if I open it up, there is not only this statistics that we have already seen, there is now a lot more statistics. So this statistics here comes from the /USR /bin /time -v. It gives you a lot of detail, lots of detail. The interesting thing that I will focus on now is this one, the maximum resident set size. So this happens to be 3.2 gigabyte and some rounding error. What is nice about this method is that this is more accurate, and also the sampling is more accurate. I showed you before, I showed you that you can do this and you can do this. The problem with Ceph and the problem with JobStats is that it samples memory every 30 seconds. And this is the reason why I made my job last 36 seconds. Because if my job lasted only for 20 seconds, I might see, it might tell me that my my job used 0 memory, which is not true, simply because the sampling didn't catch it. And since the sampling is every 30 seconds, if your job suddenly needs a lot more memory in between the sampling points, Ceph and job stats might not even detect it. But the USR bin time, according to my information, so as far in my experience, will detect it. So this is more accurate, and it will really give you the high watermark of your job. But for many jobs, it doesn't matter. So for most jobs, this is totally good enough. So what you need to remember, there is something called Slurm efficiency analysis tool, or you use job stats, or you look into your Slurm output, which includes job stats. And let's see whether I forgot any method. So back to the page, we have seen Ceph, we have seen job stats. There is also sact, which is the accounting tool from Slurm. Maybe just for completeness, I will show that, how that looks. You can do, if you know the number, you can do sact job and, well, it doesn't look like what I wanted. I think then you need to know that you can ask it for certain information. But then I need to remember that this is called max RSS, which is it is basically the memory. So this is another way to find out that this was 3.2 gigabyte. But here, I have to remember a little bit too many things. So I personally prefer the other approaches. sact jobs.ceph. This I showed you. There is another tool which I will not show. Or I can, reduce it until it fails and increase it until it runs, but it's a little bit tedious. But let's go to questions. All the methods presented so far requires to run the script and test. It seems a bit clumsy since I'm already paying for the tests. Yes. So are these tests also scheduled? Yes, they are. So yes, you pay. So it is again back to the trade-off. Very often it's worth it. In quotes, wasting a little bit of CPU cycles in order to find out what are good parameters. It's a lot more worth it for the second part, which I will show when we do the number of cores, but it's also sometimes worth it for the memory. And imagine my job is heavy, even the test might not start or having a long waiting time. And this is also a really good point. So it can be tedious for very big jobs. There are at least two things you can do in this case, which are still maybe better than guessing. Maybe I don't start with test, maybe I start with the real calculation, but then you can look at the statistics of what did my real calculation use, and then based on the outcome of my first real calculation, I will adjust the parameters for my second calculation. That's one thing. Second thing, you can contact us. If it's really heavy and the testing is very costly, we might help you put that on a different account so that you don't get penalty for it, because it's also in our interest to help you find optimal parameters. And the third thing that I recommend to do, which I do for my jobs, is that I try to start not from the big job, but I try to grow the job from a smaller example. And as I grow it, so instead of starting with the real big system, I try to cut down the system. And from this, hopefully, I can extrapolate how much memory and how many cores. But I know that sometimes that is difficult. Sometimes the extrapolation is difficult or impossible. But if it is possible, I like to start with a small example on one core, on one node, and then I go to more nodes and more cores and more memory. And as I increase the system size, I will maybe see that there is a scaling, and I can hopefully extrapolate to the real big case. But as I said, sometimes that is a difficult thing. Do the same commands apply if you want to figure out the memory usage of a GPU? Good
Can
questions.
I break in?
Yes, please do.
I was just going to add, you know, it's much better to test how much memory you need first if you can, rather than actually being unlucky, starting that heavy job running for several days, and you end up actually having said put too little memory and the job crashes. So that's also something that can happen. So yeah, it's difficult and tricky, but yeah, it's necessary.
Thanks for the good point. It's really frustrating when you have a big job and you wait a couple of days until it starts, and then it crashes in 2 seconds. So that's why I really like to grow jobs from small to big if possible. About GPU, so question 7, I don't really know. So here I admit that I don't use GPUs often enough to answer that. Hopefully somebody is in the call who knows better and can help me answer this. I think the strategies apply. So the strategy is the same. Try to calibrate if you can, but I don't know whether the same tools will work there. So what I recommend is that we will go to a break soon. I will recommend a 15-minute break. And after the break, when we come back, you can then still ask questions about memory, and we will continue answering them. But then after the break, we will talk about the number of cores. Maybe before moving on, I wanted to ask you this question. How is the tempo so far? And how is the level? So is it too slow, too fast? Is it too difficult, too simple? Very often it's both. I've been in courses where it's both too slow and too fast. So please let us know. Then we can adjust. And since I don't really see you and hear you, but I really appreciate that all of you are here, I really appreciate that we get so many questions and comments on the collaborative document. I have it open, and the more we get, the better it's for everybody. One question that I got just before the break, and I did not know the answer, but in the meantime, I could talk to my knowledgeable colleague in the corridor, and this is how you can do that on a GPU. And more details are on this documentation. So then you also can get statistics about memory utilization and other utilization. So level seems to be all right. Tempo seems to be all right. Still, please let me know if something is not all right, like font size, volume, or if the tempo changes in a not very good way. And when I go to the top of this collaborative document, I just wanted to show you where you can find these things. I will now move on to the second part, which is how do we find out how many cores a computation needs. And if you want to find the actual example that I'm using, you can, and if you have access to this account, you can find it here. But if you don't have access, the best thing is to watch what I do, ask me questions, and everything I do is on this documentation page, also the actual examples. It's a really good exercise to try what I will do now in the next 45 minutes, to try it later on your own calculation. It's a really, really good exercise. And that is choosing the number of cores. So back to my job script, and it's a different example. So the binary here, the program here is a different one than from earlier. I'm also on a different machine. It's a different cluster, but that part doesn't matter much. It's a different example, but let me open one of these. Let me show you one of these job scripts. Oh, I'm not sure whether this is readable, because maybe if I highlight it, it will be more readable. I have a different color scheme. Please let me know if this is not so readable, and then I will switch to a different color scheme. Maybe it's easier if I open it up with this editor. It will be easier to read. So here I have a job script that has a name, 10 minutes this time. And here I don't specify the memory. So I will get the default memory, which will probably be something around 4 GB. In this example, I'm really interested in this number. How many cores? 16 or 30 or 100 or 1? And it's important because the more I ask here, the more the computation will consume and reserve. So the longer it might queue, also the more it will cost. But my hope is, of course, that the more I specify here, the sooner it will finish. So that's my hope. And what I will show you is that this is unfortunately not always the case. So just increasing the number will not always mean that it will finish sooner. And we will see this example. So I have created an example here where at some point it will not pay off to add more and more and more CPUs to it. And this session here is about finding out how much do I use, how many do I need. No, I need to go outside, but I'm in the wrong. I'm used to a different editor and now I'm doing all these mistakes here. So I will not save this change. And in my example here, I already created a couple of run scripts and you can already anticipate where this is going. Because one strategy, so if I follow this documentation, let me show you the page. The number of cores. Again, I have a couple of strategies and I will show you them. We have seen job stats, it will be useful here as well. We have seen Ceph, also here it will be useful. But one of the best things to do and simplest things to do, but yes, it costs CPU time to do that, is to run a series of calculations where I take an example which is representative for whatever I want to run. And before submitting 50 calculations, I first do a calibration where I increase the number of cores and I will measure the time. And then based on the timing, we will see that at some point there is one setting which looks ideal, and we will see that going beyond will not make much sense. And I will start with that. I just want to make sure that I also see the questions. Please keep questions coming. The questions can be about the memory part as well. So back to my example, and I will really follow this page, but you can check that page later. So I have my mystery program. I don't know what is this ideal setting, but what I then often do is that I create a series of job scripts. In this job script, I will ask for 1 core. In this one, 2 cores, 4 cores, 8, 16, 32, 64, 128. You don't have to go in powers of 2. I don't know, just people who are spent a lot of time in computing and programming, they like powers of 2. And often the hardware layout is such, but not always. So on Fram, where I'm doing the test right now, if I'm not wrong, and please somebody correct me, I think we have 32 cores on a compute node. We have a different cluster called Betsy, where we have 128 cores on a compute node. Then on Saga, we have 40 cores on a compute node. But since I spent many years now in computing and programming, I like powers of 2, so that's what I do. And let me just show you one of these scripts. So this is a script where I use 1. Here is one task. I also give it different names, just that I recognize them. On Linux, a nice command to compare two scripts is called diff. So with diff, I can see differences. What are the differences between this one and this one? The only difference is how many cores I ask and the name. I also rename the output because I want to find it easier. So instead of having slurm and the job number .out, I change the output name to 2.out, 4.out, 8.out, 16.out. And now let me submit these. Sorry, I want you to see these commands as well. And I will submit them one by one. There is a way to iterate over all of them and submit them in with one enter stroke, but I don't want to now make it too complicated here with Linux, so I will do it one by one. 2, 4, 8, 16, 32, 64, and 128. Let's see whether they are running. sq --me. Some of them are running, some of them are pending. What I could do now, I could now log in into one of these compute nodes. This is something I showed you earlier with the memory. Let's connect to one of the compute nodes and see. Taking a bit of time. Okay, maybe I will abort. Not sure why this is not working. Let's try another one. Aborting again. I don't know why this doesn't let me connect. Maybe I was too slow. But what I wanted to show you, maybe let's go to this one. That if I connect to the compute node, I can run top on the compute node, and I would see that I'm using, in this case, 2 CPUs, and in this case 4 CPUs. So I'm not sure why this doesn't work, but we can do without. Still, a couple of them are running. I can see that a couple of them have finished. And we can now wait until all of them finish, and we can then compare how much time did each of these take. And while this is running, I can maybe go back to my drawing board and draw, like, what do we expect? Maybe I'll make a new, like, intuitively, you might expect that, like, when I started, I somehow expect, oops, let's take a different color. When I started with this, I expected that number of cores, as I increase the number of cores, and here it's speed up. So how much faster does my calculation finish? Speed up. Sorry, this is so clumsy. What you might intuitively expect is that as I go from 1 to etc. to many, that it goes like that. But it doesn't. What we will see, and in reality, unfortunately, you see often, is that as you add more and more cores to the calculation, in reality, it looks more like this. Somewhere it starts to flatten. And we want to know where is the somewhere. What you might also sometimes see is, for some calculation, it might even be worse. It starts to go right, it flattens, and it might even reverse. So it might even be, at some point, it might be worse to add more cores to it. It will actually slow it down. How are my calculations doing? I can see that most of them finished, except the one on 2 cores and on 1 core. They might take, so the one on 1 core, I have designed it to take approximately 10 minutes. We will not wait 10 minutes. how do I now get a good, nice overview? So in the exercise README, I left myself a little hint, but I will explain what this command does. Let me first run it and then I will explain it. So in each of these outputs, well, let me first open up one of these outputs, then it will make more sense. This is an output for the 4-core calculation. There is again lots of data. Now it's interesting to look at the used CPU time and the unused CPU time. So this part looks interesting. But the thing that I'm extracting is this thing that is called real. So this job took almost 3 minutes. And this part comes from, if I look at the same run script, because I put the command time in front of my calculation. And if I go back to this, with grep, I can now in one command extract the real time used from all the outputs and then sort them numerically. So if this looks cryptic, don't worry too much. This is just me being lazy and I don't want to open up each file separately. But let's see what we observe. So on 1 and 2 processors, they haven't finished yet. On 4 processors, it takes 3 minutes. On 8 cores, it takes 1.5 minutes. So approximately, as I double the number of cores, the time halves. This is good. I also expect that the one on 2 cores will probably take 6 minutes. And the one on 1 core will maybe take 11 minutes. It might not even finish in time. But as I double the number of cores, so here I see halving. That's good. Then I go from 8 to 16. I have doubled the number of cores, but actually the time doesn't halve. You can see that here it starts slowing down. Sorry, it starts. That's confusing. What I want to say is that as I go from 8 to 16, the time doesn't halve. Because we start to be here in this, it starts to flatten out. As I go from 16 to 32, it finishes sooner, but only 5 seconds sooner. But notice that I'm using twice as many resources. Then I double the resources again, and 30 seconds. And now observe what happens if I double the resources again, 128. It suddenly takes even longer. So there is no advantage here going. So first of all, where should we stop in this case? I think it would be reasonable to stop maybe here, or maybe here. So for this particular case, 8 or 16 is probably a good setting. It doesn't make any sense to go beyond, because we will just pay for more CPUs and we will wait longer in the queue and we will not get the results much sooner. Maybe you ask yourself, how can this be? How can it be that if there are more and more workers doing more and more work computing, how can it be that it suddenly takes longer? And this is because in this case, there is not only computation happening, but the workers that do something, they also communicate. They need to communicate and exchange intermediate results. And many computations are like this, that there is not only computation, there is also communication. And above 16 cores, 32 cores, at some point the communication part starts to dominate. And here it completely dominates the computation. If we would look in detail of where is most time spent, we would see that most time spent is here in communication. So thanks for the questions. I'm watching them. And here, maybe you have been in, if you write like an academic paper with lots of co-authors, if you add more and more co-authors, if you ever tried writing a manuscript with 128 co-authors, at some point you will see that most of the effort actually goes into coordinating and communicating and not so much into writing. So it's a bit similar with CPUs. But I'm really curious in the questions that are coming in. So one question is that it is curious that, isn't it a bit curious that the difference from 16 to 30 is insignificant, but from 32 to 64 is quite a bit. Oh yeah, that is really curious. That is really curious. Because if we just extrapolate, we would somehow imagine, we would expect that this should actually go up maybe. So this 29 is a bit curious. I could now run it again a couple of times just to get better statistics. What might also happen here is that this one is probably running on 2 separate nodes because each compute node here is only 32 cores. So it's not a completely fair comparison. So the communication pattern might be different. But I agree with you that this is a little bit surprising. But what I wanted to show here is the trend. So the trend that I see is very typical. The flattening is very typical. The reversal, you can even notice sometimes. The important part to keep here is that this kind of calibration is a good thing to do, not for every calculation that you will do, but for a representative calculation before you submit lots of very similar jobs. How about question 10? When using srun inside an SBERT script, is it the same job ID kept? Yes, it's the same job ID. But if inside your job, you can sometimes run separate steps. In my case, I ran only one. 128. In my case, I do only one thing. But you could do multiple things in a job, and then there will be a job number for the entire job, but also the individual steps will get their own step numbers, so-called step numbers. Okay. Can you elaborate on n tasks and how does it relate to number of cores? So the n tasks here, 128, I will actually ask for 128 cores. So why is it not called cores? It can be really confusing because there are, I will show you later an example where I ask for number of cores. I don't know how to answer that without being too confusing. So it depends a bit how the calculation is parallelized. Here we don't really see into the code, but when you know how the code has been written or when it is your own code, you often have possibilities to parallelize it in different ways. So there are different techniques to make use of parallel computing, depending on the technique. So if the technique is message passing interface, which is one of the many techniques, then we often talk about tasks, and then this will correspond really to the number of cores. For so-called shared memory parallelization, you want to specify it differently. And I will, in like 15 minutes, 10-15 minutes, I will show you an example where I specify it a little bit differently. And we will see that it has an effect. But it would not have an effect on this example. I'm not sure whether this was a satisfying answer, but I don't want to go too much into the rabbit hole. In this case, it would have the same effect, CPUs per task as n task. So what's the lesson learned here? I think what I wanted to show you here is that this kind of calibration, increase the number of processors, study it, is a good thing to do at least once. if the computation is really big, it might not fit into 248. You might need to start higher. It might take a very long time. So maybe try to take an example which is smaller but still representative. So if you can do this, it can be a good investment, both in human time and CPU time. But now let's look at some other strategies, and they are all listed on the documentation page. So one other thing you can do is that if you know the job number of your job, and in this case, I changed the output files to not have the job number, but of course I can still look into them. Let's look into 32. Inside, there is some statistics, but there is still the job number. And if you remember the job number, you can, and if you remember from earlier, we have this Ceph tool. Ceph only works on completed jobs reliably. So I can only use it on a job that has been completed, but I can ask, give me the statistics about efficiency for this particular job. I have used 32 cores. This was the utilized CPU. This will only tell me how many CPUs I've used, how many were busy. This will actually not tell me whether they were computing or whether they were waiting for the memory or waiting for communication. So this tool will not tell me that. But it will give me a good indication. So if you run this on your job and you see that the efficiency is 2%, then something went wrong. And the thing that goes wrong very often, what I see in my work is that, let's go back to our run script, is that simply asking for 64 cores doesn't mean that the code that I'm running can actually use it. In this particular case, I have designed the code to make use of these processors, but many don't automatically do that. Especially if this is like a simple Python script which I wrote, it might only run on one core. And you will then see that when you run Ceph on your job and you see 1%, 2%, 5%, that something is not right. And all the other CPUs, they are just sitting. And if you are unsure why is that, so like I really want to make use of more cores, you can send us an example to support@nris.no and we can look at it together. You can do, instead of Ceph, you can also do job stats like before. Job stats, if I know the job number, what was the job number? This one. Whoops, no. I wanted to copy paste. This is the job number. Job stats. You get the same statistics that you already find in the output. So also from this part, I can see that CPU utilization, in this case, 96%. But a little warning as I go, if I try that on the 128 one, 128, it looks good, CPU utilization 98%, but what it doesn't tell me is that they were busy communicating and not computing. So this doesn't mean that this is a really good setting. It's only that if you see a very low number here, then this is a bad setting. Question 16, oh, that's important. I would like to test the examples later, but cannot see them. Could you please change the permission? Yeah, so we are aware that not everybody is part of this project. And if you are not part of the project, you cannot access it. So we will make this available to you. We will email them. So you can, no, you please email Dania, the course organizer, and we will make this available to you. Alternative is that you go to this page And the examples are really following this very closely. This is actually the code that I'm now testing. So this is it's a code written in C, but you don't need to understand C to use it. So you can take this code, you can build this code using this recipe, and then you can go through this also if you don't have access to this example. So here I had a technical issue, that's why there is no number when I created this table a few days ago. So important thing from this was, it's good to do this study. You will typically see that it flattens off, even it reverses. It's good to stop before it flattens off. And often the reason why it's flattening off, or why it doesn't go nicely linearly, the speed up with the number of cores, the typical reasons are at some point communication dominates, or at some point it's something else than computation. It could be that the code is waiting for memory, or it's waiting for disk, or it's waiting for information. And now I want to show you one more thing. But maybe first I want to take this question. Does the memory usage stay the same when we use a different number of cores? Depends on the program. Really. So some programs you can add more cores and cores to it, and you don't have to change the memory settings. In some codes, both are really highly correlated. In some programs, it can even be, in some programs, it might even be reasonable to go beyond when it's really flat. Sometimes it can be reasonable to run a calculation here. And some programs do that just because they want to have a lot of memory. Because with more and more cores, you also get more and more memory. So that might be reasonable. But it's often, if you are in the situation that you use a lot of cores only because you need a lot of memory, it might be better to go to these to the high memory nodes that we have. It might be better for you, and it might be better for us. Good. And now I would like to show you one more example, which is interesting, which is on the bottom of the page. Oh yeah, this is this is something which I answered a little bit vaguely, but when you go through our examples, often we tell you that, well, if your parallelization is using MPI, do this. If it's using OpenMP, do that. So these are different strategies for parallelization. The thing is, it can be really difficult to tell whether this is using one or the other or yet something else. So I know that this is really difficult. Here we try to explain what these are and how they differ. But if it's not your code, it can be difficult to tell. You can ask us for advice. You can consult manual of the code that you are running. If you have access to the source code, you can look into the source code and look for hints. But this can be tricky. It can in particular be tricky if you try to run a code that it's a Python code or Python library or an R code or a MATLAB code. Sorry, I just zoomed in and I got lost. So you got this code from somewhere, or you wrote it yourself but using a library, and it might be really difficult to tell. So what should I choose now? Is it parallel? Is it not parallel? And sometimes it is. And I want to show you one Python example, but this is not about Python. You can also imagine that we do R here. It's really the similar question. So I will run this relatively simple Python script. And since not everybody here is writing Python, I want to explain you what it does. I create a matrix A and a matrix B with random numbers. So these are two matrices, 10,000 times 10,000 big, and I multiply them together. and I do it 5 times in a row. So we multiply big matrices a couple of times. And here I didn't want to write myself the matrix multiplication, but I'm using a matrix multiplication written by somebody else, which comes from this numerical Python library. So I'm using a library written by somebody else. And here it's difficult for me to tell, is this running in parallel or not? And in fact, it can, but it depends how you run it. And this is a case where it can be difficult to find out. Maybe you need help from us, which we are happy to give. So I will run this example with 2 different settings. So there are 2 different run scripts. And this connects a little bit to the question that was raised earlier. If I run it I will run it on one node with 4 tasks. And then I will run it with settings that look really similar. Both settings will consume 4 cores. But what I will see is that the timing is really different. So let me test that. And I will go for this, I will go back to Saga. So let me disconnect from Fram and let me SSH to Saga. Best way to participate now is to watch me do that, because you can try that example later. I will make a new folder example. Sorry, I also need to, here I need to make sure that you can see my commands. Just a sec. Teaching. So I do some trickery here to make sure that you can see my commands. All right, now everything I type, it will also show up here. I will create a new folder, example. I go into the example and I will copy this example in it, which is a Python script, example.py. I will paste it in. Let's save it. And now I want to try these 2 run scripts. I will call this run script A. And the thing I need to fix here is this part, which 9970 for this particular course. I give it 5 minutes. I give it a certain amount of memory. Here I'm more interested in this part. Save, yes. And I will copy it into a run script B, where I use similar settings, but instead of tasks per node 1, I will use, instead of 1 task and 4 CPUs per task, I will use 4 tasks. It will consume the same amount. Oh, sorry, both will use 4 cores. Save, yes. Now let me submit A. It's running, good. Let me submit B as well. Both are running. And then we will compare timing. And now I'm catching up with questions here. I have a feeling that everything is answered or being answered. So thanks a lot for those who typed the answers. Still running. I think I designed it to finish within a few more seconds. The one with the lower job number was the first one I submitted. Still running. Demo effect, but I think it will finish soon. So what I will hopefully see is that one of them will finish a lot sooner than the other. Suspense. Chance to ask more questions, so please do that. Okay, one of them finished, which is the one that I started earlier. And it took approximately a minute. How about the other one? The other one is still going. And what was it? The numbers were this one and the 82. And I will now compare with Ceph, but I need to wait until the other one is finished. I can already look at the first one. So here, completed after 1 minute. Well, so what is this thing here? 3 minutes. How? So did it take 1 minute or 3 minutes? It took 1 minute in wall clock. So the clock on my wall, so the wall or on my watch. So this is the time that I see. But the CPU, it used 3.5 minutes in CPU time because I have used more than one CPU. More than one CPU was busy. CPU efficiency not amazing, but 70% of the CPUs were busy doing something. This is the one that matters most to you as a researcher because this is the time that you wait, but this is the time that you pay. This one is still running. I think it will take maybe 3 times longer than the other one. So I expect the second one to finish 3 times around 3 minutes. So the same job, a little bit different settings. And what is the explanation? The explanation is, and if I show you the run script, I run this Python example. This command here is a way to print all so-called environment variables. With environment variables, you can adjust certain settings. And there is an interesting one which contains num threads. Maybe it will make more sense if I look into the output. So in the output, I'm interested in the environment variable that contains num threads. There happens to be one. There happens to be an environment variable called OMP num threads, which does the calculation that please use 4 threads for this. What the OMP stands for OpenMP, and I know that all of this stuff is super technical and confusing. And why is this suddenly called threads? I was all the time talking about cores. I think for a beginner, this is almost impossible to know. But in this case, the job sets this for me because I have asked for one task and 4 CPUs per task. It sets this variable for me. And this Python code happens to use this and makes use of it. The other calculation doesn't set the variable. And my Python calculation doesn't know that it has 4 cores available, and it will only use one. And I don't expect anybody to remember these terms. But what the morale of the story is that, now both finished, that sometimes it can be really difficult to tell whether something can make use of parallel environment or not, and how to best set this environment. Here I need to know that either I need to know that I need to set a certain variable, and hopefully the code tells me that, or I need to be lucky. In this case, I was lucky and it set it for me. If I now go back to the Ceph and compare the two, the one calculation finished after 1 minute, the second calculation finished after 3.5 minutes. This one, the first one, made use of CPUs, approximately like 3 out of 4. In the second calculation, 25%, because one CPU was doing the work and all the 3 CPUs were watching. And a similar experience you can see also when you get on not just Python script, an R script from somewhere, and MATLAB script. So here you need to go into the documentation. Do they give advice on how to make use of parallel computing? Here, what I need to do, I would have to go into NumPy documentation and read about how do I run NumPy most efficiently on supercomputers. Not easy, but it can make a big difference. So here on many cores, it can be a factor 10 if I want to. So I think this is everything I wanted to demonstrate, but I also wanted to, so please keep questions coming or comments. We can look in more detail. I can maybe show other examples. What did I forget? So this is everything I had planned. So to summarize, if you have a big series of calculations which are similar, calibrate first. If you should calibrate only one thing, then calibrate the number of cores. But if you can, also have a look at the memory. You can calibrate both at the same time, because you can look at the statistics from, while calibrating number of cores, you can look at the statistics of how much memory was used. And don't use too many cores, because just asking for 300 cores does not mean that the computation can make efficient use of it. Scaling to very many cores, so going to hundreds of cores, thousands of cores, needs really advanced expert knowledge. We have experts within NRIS who do this every day. So if you have such an example and you need assistance in scaling up really beyond 100 or 1,000 cores, please get in touch and we can work with you on making this work. And then please, before you leave, give us feedback for the day. It's anonymous and we really appreciate honest feedback. So tell us one thing that was particularly good. So what did you like most? But also tell us one thing that we should change or improve or replace, or just so that we have a chance to improve it. This is a series of lessons, and maybe Daniel can tell me how often they are. Do we do that every few weeks, once per week, once per month? I forgot, sorry.
We are trying to do it once per month, except April, because next event will be on different topic, how to install software on the cluster as a user.
Yeah.
So that will be on March 7th, a Thursday, 10 to 12:15. And there will be other instructors who will be giving that instructions. And the third and last one will be in May. That's mostly on file transfer and data storage and best practices on how to store data. So April, we have an HPC onboarding course for the new users. And so that is where you will learn more about the Slurm and all, how to schedule jobs and all. And there is one more course we are collaborating with Code Refinery project about HPC workflow. We will come up with the more information on the event page soon. That's also 2 events in April and 2 events in May. So that's why we are not trying to have one more event on this best practices series in April. We have a lot of events coming up here. And thank you so much for joining us today. And your feedbacks are valuable for us to improve next time.